Hello everybody, my name is Jonas. I work in the Blockstream research group and I'm going to talk about secure protocols on top of BIP Taproot. So most of what I'm going to talk about is a collaboration between many people in the Bitcoin community, including my colleagues at Blockstream. BIP Taproot is an idea that was recently posted on the Bitcoin mailing list that proposes some improvements for Bitcoin. But I want to start with a disclaimer saying it's not at all certain that a BIP Taproot soft fork activates in its current form or at all. This all depends on community consensus. Although the feedback so far hasn't been very negative yet, so that's a good start. And at Blockstream, we are interested in this because it makes many things that we do cheaper and more fungible, including our Blockstream Green multi-signature wallets, sidechains, and our Lightning implementation. So let's start by looking at how BIP Taproot works. So assume we have some policy where a coin can be spent by an authorization from a single party with a single key. So the only thing that you need to do in order to create a script pub key is you push the number 1 onto the stack, which now indicates that this is a witness program version 1 as opposed to version 0, which is already defined, and you push your public key onto the stack. Now things get much more interesting with BIP Taproot if you have more complicated policies. So for example, if you have the policy that a coin can be spent either by an authorization from a single key or a Bitcoin script or another Bitcoin script or a third Bitcoin script. So what you do is you take your single pub key, which is in this context now called the internal public key, and you take your various scripts and build a Merkle tree out of it by recursively hashing the leaves and the inner nodes until you arrive at some root. Then you use a construction known as pay-to-contract in order to take these two ingredients, the internal public key and the Merkle root, and create a new public key, which is now called the Taproot output public key you see on the right. Now what happens if you want to spend such an output when you see it? So there are essentially two ways for how to spend this output. There's the key spend, which means that you just provide a BIP Schnorr signature for this public key that is directly in the output, or you do a script spend. And you do that by first showing the script that you've committed to. You show a proof that this script connects to your Merkle root. You show that the Merkle root is in the output, was committed to in the output public key, and of course you also provide the inputs to the script in order to satisfy it. The important part is that the only thing that is in the output is in the public key, and you only need to decide at spending time which method you need to use. So we are working on this in order to allow developers to already use this. And we do that by extending the libsecp library, which was originally written by Peter Weller for Bitcoin Core. And one of the main ideas behind it is that it should be difficult to use insecurely. Because it's used in Bitcoin Core, it's value reviewed and tested, it's fast, it's mostly portable, and it's free of timing side channels. There's also a lot of options if you want to use various bindings. libsecp is written in C, so for example, pretty mature is the implementation from the Rust Bitcoin project, which requires very few dependencies, not even a standard library. But the ingredients that you need in order to support BIP Taproot in your wallet are not merged in libsecp yet. They are only pull requests. So Blockstream has its own library called, it's a fork of libsecp, it's called libsecp ZKP. ZKP stands for Zero Knowledge Proof. And this library has a few advanced schemes, for example, range proofs for CTs, rejection proofs, and we've also merged Schnorr signatures and a music scheme. And we just this week released Rust bindings to this library, so now you can use this in a type-safe way. This beta version right now only supports Schnorr 6, nothing more, but we're going to change that in the future. In general, if you want to use this library, the first thing you need to do is to read the documentation. So the documentation is in the include directory in all of these C libraries. But I'm going to talk about some of the pitfalls when using these libraries in a moment. Okay, so the minimum thing you need to support for BIP Taproot is how to make Schnorr signatures, so let's talk about that. On the right side, you always see links to either pull requests or modules, so later, if you look at the slides, you can just click at them. So a Schnorr signature is, in general, very similar to an ECDSA signature. A Schnorr signature is 64 bytes, consisting of two elements. One is an encoding of a point, 32 bytes, and the other one is just a number. And the point is usually called R, and the number is usually called S. And R is also known as the public nonce. And this has many implications for security, because a nonce is called a nonce because it's a number supposed to be only used once. So this isn't a problem at all if you just use Schnorr-sig in a regular way, where you just create a signature and you verify signature has nothing to do with this. So this is only about signing. This is the same as with ECDSA. Your nonce is generated deterministically from the message, such that you have this guarantee that if you use a different message, you will use a different nonce. So you don't need to do anything. This also means that you never actually have to use a particular nonce. So for example, in a discrete lock contract or in single show signatures where you have to commit to a specific nonce, you just sign twice or multiple times because you will always be using the same nonce. Schnorr signatures also allows you to do batch verification. And this means that you verify a batch of signatures at once. And this is faster than verifying them one by one. So for example, if you have 400 signatures with our implementation, it can be verified in half the time than it would take to verify them one by one. But using this batch verification, you don't really know. If the batch verification fails, you don't know which signature was responsible for it. And this is also the reason why batch verification may not reduce your worst case cost, because you need to know who actually was dishonest in this protocol, or perhaps the attacker could send a signature such that it wouldn't be in your batch or something like that. So what we're also implementing in libsecp, this is independent of Schnorr signatures. It's also a problem with ECDSA. This is based on an idea by Greg Maxwell. So a problem that's right now, we have right now with hardware wallets is that there is the possibility to exfiltrate a private key through a nonce. So let's say you have a hardware wallet and you do a firmware update, and this was a bad firmware update. So suddenly your hardware wallet is compromised. So generally, the only thing that the hardware wallet has to communicate with the rest of the world are signatures. And there is actually a way to put a private key into the signature using the nonce. So the general idea how this works is that both the hardware wallet and the attacker generate the nonce in a very similar way, except for a few bits. And these bits need to be grinded by the attacker, and if there's actually a match between a nonce in the blockchain and the attacker's computation, then the attacker knows a few bits of a nonce. And this is an encrypted channel, so no one else can see it. So the idea that we're implementing in libsecp is that you use a construction known as sign to contract, where you enforce that there is some randomness in the nonce. So the host computer enforces this. The way this works is that the host draws some randomness, sends a commitment of the randomness to the hardware wallet. The hardware wallet derives their nonce with this commitment and secret key and message as usual. The host replies with the randomness, and then the hardware wallet uses the sign to contract construction to create a special nonce that includes this randomness, and this totally randomizes this nonce. Now, when the host receives this signature, the host just needs to check, is my randomness actually included? If not, the signature is not sent out to the blockchain, and probably some alert is raised. The alternative is to create a music key aggregation between the hardware wallet and the host, but that's currently very difficult for hardware wallets to do, which we're going to talk about later. If you want to use more interesting policies with BIP Taproot, another thing that you have to support is this pay-to-contract construction, or tweak add as it's called in libsecp. So again, what this does is it takes your internal public key and it takes a Merkle root and it computes this Taproot output key. So mathematically what this is, if your internal public key is P, is fairly straightforward, then you just add the hash of a constant prefix that's defined in BIP Taproot, the internal key and the Merkle root times the base point G, and you receive your new Taproot output point. So in libsecp, how this looks like, this is just a function called ec_pubkey_tweak_add. You give it a secp context, you give it a public key, and you give it the tweak. And the tweak is the hash. And that's all there is to it. However, there are some problems maybe with fungibility, because this, if you use a script path span, this already reveals quite a lot of information. So in general, you really want to avoid using the script path at all. So if you have some kind of multi-party contract, you generally try to get all parties to agree what the state of this, what the end state of the contract is, and then let everybody sign using key aggregation instead of having to fall back to these script paths. Also, what's still the case, as has always been with Bitcoin, never reuse the keys. This holds both for the internal key, but also all the keys that you eventually have in leaves. So the script path, I think, basically will reveal a lot of information about which kind of wallet you use, because it at least reveals the minimum depth of the tree. It also reveals a script which can have a lot of identifying information. And another thing you need to take care of is that you always have sufficient leaf entropy, which means, for example, you have always a different public key in a leaf, because otherwise you wouldn't allow an attacker to just brute force search your leaf script, because there's no additional blinding or randomness applied to the individual leaves. If you want to do multi-signature things with BIP Taproot, you have quite a few options. So one is to use this new opcode called checkDLSAdd, which is basically a replacement for check multisig. Check multisig would be deprecated in this version. And the advantage of checkDLSAdd is that it's batch verifiable, which check multisig is fundamentally not. And it's also BIP Schnorr compatible. Another thing you can do is you can use key aggregation. I've mentioned it a couple of times. What this allows you to do is to encode an n of n signing policy in a single public key and a single BIP Schnorr signature. So you can use that as the Taproot output key. This has the advantage that it's more fungible because you never see a script path, and it's definitely cheaper because you only have a single public key and a single signature. But the main problem is that this is an interactive protocol where you have multiple parties and they send messages around in multiple rounds, and they need to keep state. You have a few key aggregation options. So even with BIP Taproot, there is right now the possibility that there are some newer papers which explain how to do some of the key aggregation stuff with ECDSA. So you can use pay-to-witness pubkey hash for maximum fungibility. But this is relatively complicated. This uses new assumptions. It's relatively difficult to get right and avoid timing side channel attacks, and it only has 80 bits of security, which may be okay for many use cases, but still it's not the usual 128 that we want. With BIP Taproot, you can use music key aggregation. The idea is that your the final public key is just the sum of the individual public keys, but each individual public key is multiplied with the so-called music coefficient. And the music coefficient is the list of all public keys in the set and the index. You also have the possibility to not use music key aggregation, so the alternative is to just add up your individual public keys, and then you need to provide a proof of knowledge that you know the secret key to this public key in order to avoid key cancellation. But this has a problem because now a single party can just add a taproot tweak without that being noticeable. And this taproot tweak could have a script such that this one malicious party could just on their own spend the coin. So BIP Taproot right now recommends that in such a case you would always add a script path, but this script path would be unspendable. So this is, in general, how music looks like. The function names here are very similar to what we're doing in our implementation. It's 3 rounds. So you start with initializing your session, and for that you need a fresh, new session ID that you've never used before. You create a nonce commitment. You exchange nonce commitments. That's round 1. Then, if you have all nonce commitments, you get your public nonce. Then you exchange, all parties exchange their nonces. When they've received the nonces, they set the nonce, which means that they check whether the nonce matches the commitment. If not, the protocol needs to be aborted. They combine the nonces and then they partially sign to get a partial signature, exchange the partial signatures, combine the partial signatures, done, we have a final signature, a BIP Schnorr signature. So our implementation is safe if you do 2 things. You are never supposed to reuse a session ID, so you need randomness or an atomic counter that can never be reused. Unfortunately, deterministic derivation is very hard for music, and you never copy the state. Otherwise, you might have problems with nonce reuse, which would leak your private key, or you are vulnerable to active attacks. So when you look at this and the 3 rounds, you might think, ah, that's horrible, now we have additional rounds, but maybe in particular protocols it's not all that bad, because probably your protocol already has existing messages and you can just attach parts of the music protocol to it. So if you have, let's say, a client hello message, you can just attach a nonce commitment right at the start of your protocol. You can also run multiple sessions in parallel, that's no problem. So you would have an initialization phase where you pre-share nonce commitments and nonces, and then only when there's a message that you want to sign, you just need to exchange the partial signatures. You can also have a fixed number of parallel sessions, let's say 3, where you have session I, which is in the partial sig state, session I+1, which is in the nonce state, and session I+2, which is in the nonce commitment state, such that a single message round trip would result in a partial signature. Unfortunately, using music with offline or hardware wallets is very difficult, because probably when you use your hardware wallet and you have these multiple rounds, your hardware wallet will lose power, so you need to move the state to some persistent medium. And this is basically a copy, so very dangerous, because now you need to ensure that there's only one instance of your state there ever. Therefore, in our implementation right now, we don't really support serializing the state. But remember, this is only for signing. For online devices, for example, a Lightning node or whatever, this would be very quick, and if you would suddenly shut down during signing, then you would just start again. You can have kind of a single session, like you move it to persistent storage, and then you somehow ensure that there's only one state still, and then you load the state. But then you need to travel to your hardware wallet, which may be in some Swiss vault for every single signature, and your transaction might require many signatures, so it's not really workable. There is some hope and research effort into deterministic nonce generation for music. What this means is that every party just generates the nonce similar to how it works right now in the single party case by just deriving it from all public keys and the message. The catch here is that you also need to prove that you've done so correctly, and you need to verify that everyone else has done so correctly. But if there were such a scheme, you wouldn't require randomness, you wouldn't require a state, it would be only 2 rounds of communications. But you still want the zero knowledge proof, proving that you've derived your nonce in the correct way, to be efficient, because this needs to be done potentially on a very low power device. And also, obviously, this adds code complexity and a lot of, potentially a lot of places where there could be bugs or vulnerabilities. I think I'm going to skip this a little bit. I just wanted to say here, my main message is that our implementation also supports adapter signatures, so you can do things like scriptless script atomic swaps or scriptless script lightning. The main gotcha here is that you always need to partially verify partial signatures, which you don't have to do in general. So another thing I wanted to talk about is blind Schnorr signatures. This would also be enabled by BIP Taproot, because BIP Taproot supports Schnorr signatures. So blind Schnorr signatures are an interactive protocol between a client and a signing server, and the main idea is that the signer does not know the message being signed, but the result in the end is a BIP Schnorr signature. So you would have like a user, Alice, and they have a cosigner, maybe some service, but Alice doesn't want to tell the cosigner which exact coin she's spending, so she just gives a blinded transaction to the cosigner, potentially some proof for second factor authentication or velocity limit or something like that, and the cosigner returns a blind signature. Alice unblinds a signature, and now she has a signature on a transaction from the cosigner. Now, the problem with blind Schnorr signatures is that they are actually broken. So they are vulnerable to Wagner's attack, which means that with 65,000 parallel signing sessions, you can forge a signature with only 2 to the 32 work, which is very low. And they can't be proven secure in the random oracle model. So the gist of this is that if you just need blind signatures, for example, for your eCash scheme or whatever, then don't use blind Schnorr signatures. It doesn't make sense. There are way better schemes out there which have provable security and have many more features. But if you need blind signatures for Bitcoin transactions, you are essentially stuck with blind Schnorr signatures. I think this whole field needs a lot more research. There are some ideas for how to prevent Wagner's attack. So one has essentially a 128 communication blow-up where the client blinds a single message with 128 different blinding factors, sends all of them to the server, and the server then just randomly picks one of them and returns, signs it and returns it back to the client. So in conclusion, BIP Taproot is a substantial efficiency and fungibility improvement. It allows building lots of interesting protocols on top of it, but still simple sending remains as simple as right now. There are a few changes, but mainly you need to somehow create Schnorr signatures. But other than that, it's very simple. You can use libsecp libraries for this, for the cryptographic primitives. BIP Taproot doesn't change anything in the cryptographic assumptions. So there's still the discrete logarithm assumption in place, which is nice because verification is pretty fast and it's a well-studied problem. The problem is, though, that this often requires, as we have seen, interactive protocols, and they have challenges on their own. At least these challenges are off-chain, but still this is a very interesting problem. We haven't talked about K of n threshold signatures because just due to the time constraint. There is a pull request for this to libsec PZKP right now, but we're working out subtle issues with denial of service attacks. And my main message to you is please try to break it or use it, or write toy implementations and compare them, because there is still a lot of work to do in this whole field. Thank you.
I have perhaps a naive question. You had a slide pretty early on with a host and the hardware wallet, and
yes,
it provides randomness. And since the host picks the randomness, what prevents the host from reusing randomness and extracting the key?
So in this case, both parties provide randomness to the nonce, not only the host. Okay, perhaps a question from Signal? No?
I was just going to add to that last question. What if the host is also has malware on it, but then I guess it could just, like if both the host and the device have malware, then I guess the device would just give the private key to the host and the host would just send it to the server.
So it doesn't protect against, it doesn't protect in this threat model. Okay, then, thanks again.